In this video, I want to go over a few more examples of ionic compounds and determining what their chemical formula is when we just know what the elements are, or when we know the name, or if we know the chemical formula and we want to figure out what are the charges on the ions that we actually have. So let's start with an example of potassium and oxygen right here. When we're given two elements, the first step is always to identify which of these is the metal and which is the non-metal. So looking at my two elements, potassium, I can use the periodic table and just scan and look for potassium. I'm going to find that that is K and it's a metal. And if I look for oxygen, it is a non-metal element. I'm using metal and nonmetal as kind of a shortcut to decide which will be my cation and anion. I could also look and compare their relative ionization energies or metallic character or electronegativities to determine which one should be the cation or the anion. Typically, metals form cations. So we are going to have potassium be the first and then oxygen the second, because my potassium will be our cation. And now I'm going to use the periodic table to determine what the charges of these are. And potassium is in my first group. And oxygen is in group 6 of my representative elements, which are going to be those first two columns of the periodic table and then the last 6 columns of the periodic table. I had a count in my head. All right, well, anything that is a group 1 metal or group 1 is typically going to form a +1 charge. It only has one valence electron on the outside of its electron cloud, and it'll easily lose that electron to have an electron configuration or structure that's similar to a noble gas. So because this is group 1, that's going to be, it has one valence electron, that's going to equal the charge. So I'm going to write that down. I'm going to have a potassium with a +1. Now you can write +1 or you can write plus. If it's plus, it's at least +1. Now my oxygen is in group 6. It has 6 valence electrons. And I am going to determine its charge by taking 8 and subtracting its group number of 6 to give me 2. So I'll have a magnitude of charge of 2. And it'll be negative because it's an anion. So I'm going to write that here. My oxygen will have a -2 charge. All right. Now at this point, I need to figure out how they're going to combine, in what ratio, to form a neutral compound, something that has an overall charge of 0. One way to do this is with the Crisscross Method, which is I take the magnitude, so this is +1, and make that the subscript on my opposite element. And this is just a algorithm, if you will, for solving these. The other way to do this is to compare my charges and determine which one I need to have more of to balance out my charges. So if I would do that, I would say, well, I only have +1 for my potassium and I have -2 for my oxygen. So I'm going to want to multiply my +1 on my potassium to equal, the opposite of my -2 charge over here. So in this case, I'll see that my X needs to be equal to 2 to be able to balance out my charge. So that way I'll have a +2 charge for my cations and a -2 charge for my anions. So that's going to show me, or the crisscross, I take that 2 for my oxygen and it tells me I need 2 of these potassium, and I have a +1 for my potassium. It tells me I just need 1 oxygen. It's going to give me a chemical formula that is 2 potassiums and 1 oxygen, or K2O. So this is an example when we have representative elements. First 2 columns, last 6 columns. If we have something in between those two in the transition elements, or even in the post-transition elements, which are the metals that come after the transition metals in rows 3 and below, then those atoms can have multiple different charges. So we won't know exactly what it can do until we get more information. And here, that form of information is coming from, or that information is coming in the form of the name of our molecule. So we've got manganese 5 chloride. This is telling me that my manganese has a +5 charge. And it doesn't tell me anything about the chloride other than it's the anion. Because my manganese comes first in the name, it's the cation. And when the chloride comes second in the name, that makes it the anion. So we're going to take our cation and write it out. Our manganese element symbol is Mn. And if it has a +5 charge that the name's telling us, we'll add the +5 here. Our chloride ions, we will have to determine that from the periodic table, just like we did in our previous example. So if we look at the chlorine atom on the periodic table, we'll see it's in group 7. It has 7 valence electrons. So to determine its charge, I'm going to take 8 and subtract that group number for 1. That means my anion will have a magnitude of charge of 1. So it'll be a -1 value. Now, again, I can perform the crisscross rule if I like. And if I did that, I would say that 5 from my manganese would become the subscript of my chlorine, and that 1 on my chlorine would be the subscript of my manganese, or manganese Cl5. If instead I just wanted to work this out algebraically, I could set this up so my, I know my manganese has a +5 charge and my chlorine has a -1, and I need this to be the opposite. That -1, that 1 value is smaller than the 5, so I'll multiply that by x. If I solve this equation, I'll get x equals 5. So that would tell me I need 5 chlorine for every 1 manganese. All right, now I want to take a look at working backwards, where and here's my example, manganese oxide. So in this case, I have the chemical formula, and my question is, what is the charge on the manganese? So manganese is a transition element, so it can be lots of different things. So I can't rely on the periodic table to determine what that charge is. Instead, I need to look to the oxygen. This is a representative element. So I can determine its charge from the periodic table. It will reliably always be the same. It's in group 6. It has 6 valence electrons. That means 8 minus 6 will give me the magnitude of charge, so it'll be 2. It's written second, therefore it's an anion. So that charge on the oxygen is -2. I'm going to use that information to determine what the charge is on the manganese. Now, we could do the reverse crisscross rule, where we go that the 2 subscript after the oxygen would tell me then that I had manganese +2, and the 1 subscript on manganese would tell me I had a charge of -1 on my oxygen. I would need to double check this, because that oxygen with a -1 charge, that doesn't make sense when I look at the periodic table. And so really this isn't going to get me directly to the right answer. I'm going to have to manipulate it a little bit. I'm going to have to recognize that this -1 charge isn't what I would predict from the periodic table. Let's work from the oxygen being -2. I know that I have a subscript of 2. So if I have 2 oxygen and each one has a -2 charge, I have a total of -4 coming from the anions in this compound. I have only 1 manganese. So all of the positive charge to balance out that -4 is going to be on 1 manganese atom. So it'll be the opposite of that -4, will be +4. So I'll have manganese +4 in this molecule. That means that if I was looking at my reverse crisscross method, I would need to multiply both of these by 2 to get to a manganese +4 and an oxygen -2, or that oxygen -2 makes sense.